So I think previously I had talked about my own personal opinions on sigma, and what's the likelihood, when we were doing confidence intervals, I said, what's the likelihood that we would know a standard deviation of a population without knowing mu? That seems pretty unlikely, right? And with significance testing, I think the same thing is true. What's the likelihood that we would know a standard deviation of a population, and yet we're making a significance test about how likely an event would happen with this mu that we're assuming or we're given. So it's not likely at all, I think, in the real world. So what we probably, when we're doing counts in the real world, would be more likely to look at this. Now, we've seen this standardizing formula back in chapter 9, right, where we didn't have sigma, so we had to use our sample standard deviation, that's S. And when we use the sample standard deviation, we have to pull our, it's not a z-score anymore, it's a t-score, right? It's a t-star or t-value. So a couple things to remember. T is not normal. So why do we have T in the first place? Well, here's why. What we discovered, not me, but humanity has discovered over the past, is that if you just simply replace S and use the Z table, your answer's a little bit off. Not exact, not great. It's off enough to be a concern. So the T chart, the T distribution table, was created to address that deficiency. So whenever we're using S, we've got to use T. Remember, what else about T? Is there anything else that we need to remember? Degrees of freedom, that's right. So whenever we're using T, we need to use degrees of freedom. Which the degrees of freedom are always going to be n minus 1, or round down if you're using the table. And in this problem here, x bar and S are calculated. So you'll probably, in many cases, be making a list using 1-bar stats to get x bar and S. You will see sigma x bar. Don't ever use that in the calculator. We only use S or S of x. And this is also S of x in the calculator. Right. Okay. So the calculation itself isn't really all that different than what we've done in the past. But since it's a significance test, we're still comparing it to some alpha, some line in the sand, if you will. Let's look at an example. And this doesn't have sample values in it at all. This is sort of after you had, if you had already standardized. Let's say the null hypothesis here is that mu equals 1. And the alternative is that mu is greater than 1. And let's say that we're given that the sample size is 21. And the calculated t value is 1.97. So we're looking at a more than problem where t is 1.97, somewhere over here, and we're looking to see if our value would be in a tail or not. So here's what we can do. Hang on, before we go any farther. You guys still have your table Ds? Anybody need a table D? So what we're going to do on table D is we're going to look for this 1.97 value. So if n is 21, our degrees of freedom are 20, right? Yep. So I'm going to look on table D at 20, and I'm looking for the closest value to 1.97 as I can get, or between values, most likely. Because as I'm looking over, 1.97 is going to fall between 1.725 and 2.86. And the p-value, the upper tail probability, is between 5 and 2.5%. So I have that this falls between, let's see, what were those values? 1.725 and 2.086. Which would put it between 0.05 and 0.025. So this would be our p-value, somewhere in there. Would we reject or fail to reject the null hypothesis with a p-value between 5 and 2.5%? Yeah, it does. It depends on what alpha you set, doesn't it? But say 5 or 10%, this would be significant, right? So we would reject the null at 5% or greater for sure. If it was less than 5%, then we're not sure, right? If it was 1%, then definitely we would fail to reject. But we would reject the null at 5% alpha. Let's write that down. And we would fail to reject at 1% and conclude that the alternative is correct. That mu is greater than 1. Whatever the example, or whatever the topic is here, we're not sure. So let's look at how we could calculate that percent exactly in the calculator, because there's a function that will allow us to figure out exactly where it falls between 5 and 2.5%. By the way, the table values are just fine. So by going to the table and finding that it's here and then comparing it to alpha, you don't have to go to the calculator, but there is a calculator calculation for this. So if you go to second vars, that's your distribution, and then number 6 which is your TCDF. So it's the remember what CDF is up to that amount but it's a T value, so it's sort of over that amount really in this case. So I'm going to go to TCDF. Here's where this is a little strange. Let me clear this. I can't clear this out. In my drawing here, I have 1.97 and I'm looking for the area above 1.97. Where does this curve go? I mean, what's the highest standard deviation? It does. It goes forever, right? Essentially, that's infinity. But have we ever seen a standard deviation that was like 10 standard deviations away from the norm or 100 standard deviations away from the norm? Right. We haven't. So what we're going to do is we're going to put this number in as the lower number, 1.97. And for the upper number, we're going to put just some large number of standard deviations. I'm going to say probably 5 or more is probably plenty, but let's put in 10. And our degrees of freedom in this problem would be 20. So does that make sense as to where we're getting the 10, right? We're just picking some inadvertent, really big standard deviation where the likelihood of being more than that is so small it's effectively 0, right? So we'll paste that. And so that percent is a little bit more than 3%. So we get a pretty accurate p-value on that. Again, this is the end of a problem, right? We didn't have to do, in this example, we didn't have to calculate t. It was given to us. But in a normal problem, we'd have some set of values. We would put them into the calculator, find s and x bar, and then plug them into here to get t, and then you can go from there. Let's see. Let's look at an example from the book. This is everybody with me? This is the first problem in the set, 12.3. It's on page 775. I'm sorry, 745. And it's a one-sided t-test. Very similar to the example that I just gave. They give us a null and alternative hypothesis. It says n is 15. And t is 1.82. So the first question on this one is, what are the degrees of freedom? 14, yeah. So degrees of freedom is 14. And then it says, give the two critical values of t star from table C, they're calling it C, for us it's D, that bracket t. What are the upper tail probabilities for the two entries? So that's where you go to table D and you're looking for 1.82, the t value of 1.82, so I go to 14 first, and I look across. 1.82 is going to be between these two guys right here, 1.761 and 2.145. So this is t is between 1.761 and 2.145. 1.82 falls between those two values. And then C asks us between what two values does the p-value fall? Well, to get that, I go back to where I'm at here and I just simply look up. What is my upper tail probability? It's between 5 and 2.5% again. So the p-value is somewhere between 5% and 2.5%. And D said, is the value, the t-value, 1.82 significant at the 5% level? So we're saying that the p-value is between 5% and 2.5%. So if we set alpha at 5%, would this t-value be significant? Is p less than alpha? Yeah, if alpha is at 5%, it's actually less than or equal to. Even if it was equal to that, which it's not because it's between these two, it's going to be less than 5%. This would be significant. So for D, at alpha equals 0.05, t is significant, which means we would reject the null and conclude that the alternative is true. What about at 1%? Is t still significant at 1%? No, because it's between 5% and 2.5%. It would have to be less than 1%. It's simply not. And I know this isn't part of the problem. Let's add an e to this, and let's calculate with your TCDF. Let's calculate the probability for this information. So we'll go to second bars, your distribution, TCDF. It's still a greater than problem. So mu is greater than, so my lower number is going to be 1.82. My upper number is going to be some number of standard deviations that's large. Okay, 10 is more than enough. Degrees of freedom in this case is 14. Paste. Let's see what we get. So we get about 4.5%. 0.451. So the true p-value and that's using TCDF 1.82, 10, and 14.